Welcome back to Bionics of Surfaces. Today I'm interested in the interaction between molecules. So we're going to start off with this argon, which is not going to interact with anything because it's not got any bonds. And we'll have to bring something up close to it to try to make it interact. Let us start off by bringing up something that's charged. So if we do that, so the plus here, we're going to distort our argon. So in this case, we've got argon, which I've drawn kind of wrongly. The nucleus is too big, really, in comparison to the electron cloud. The negative charge is spread out over here, and the positive charge is spread out over the nucleus, but it's very small in comparison. From outside, it looks neutral, but if we bring along a positive charge close to it, we will distort the argon like this. So what we've now done is we've pulled the electrons towards the positive charge and we've pushed the positive nucleus away from the positive charge, which generates a thing called a dipole. A dipole has two poles. So a magnet is a dipole, it has a north and a south pole, but in this case we've got an electrical dipole which has a plus and a minus end, and in total is zero. In this case, the total charge is zero, but it has a negative charge, negative pole over here and a positive pole over here, which we normally draw as an arrow with a cross on it. So I'll draw that. We normally draw as an arrow like this with a cross on its tail. So that is what we've generated with our positive charge. And what we find is, because the negative end is closer to our positive charge, that the argon will now be attracted to the positive charge. If we take something that already has a dipole, like this, whatever it is, it's a plus connected to a minus, and we haven't defined what that is yet, but it's something that already has a dipole, then we can attract two dipoles together. One of them a permanent dipole, and this one, which is a temporary dipole, because as soon as we send this away, then it will return to being normal argon, which isn't charged and it has no dipole at all. So the dipole means it's got two ends, a plus and a minus. What happens if we bring another argon up? And the other argon will see the dipole, the temporary dipole, on our first argon atom, and it will respond accordingly. So it will see this negative end, and that will push its electrons over to this side and attract its nucleus to this side. So now I'm going to rub it all off and just draw that, because otherwise we'll have too many things. So now what we've got is a situation where this argon that was temporarily polarized has now polarized another argon atom. And as you can see, there's my head, the two dipoles agree with each other. This positive end is going to attract this negative end, and they're going to stick together. That's not the only force present here, because we've got effectively the center of charge, like the center of mass, of the electron cloud is here, and the center of charge of the protons is here. So we've got a plus and a minus attracting one another inside the atom as well. And that's going to be a force that will act to destroy the dipole. So let's let it do that. First of all, on this left one here. So it would obviously go to back to being normal argon. I'm going to move the nucleus. That's not what normally happens, because the nucleus is heavier than the electrons. Typically the electrons move, but for the purposes of not running out of space, I'm going to move the nucleus closer. Yeah, otherwise they'll crash as well. I'm going to move the nucleus closer. It's not what really happens. So now our argon nucleus, or in effect the argon electrons, are moving back to the central position, but they've now got up some kind of momentum, and there's nothing really stopping them, particularly at this point, because there is no electrical force. Until they move past, there's no restoring force to push them back the other way. And so the electrons are obviously going to shoot straight past where they would be, their normal equilibrium position, and appear on the other side. Now what we've got effectively is our dipole has disappeared, but a new dipole has appeared in the other direction, And that will obviously affect the other argon atom. And of course also, because they're both argon atoms, the elasticity and strength and the resonance, so the frequency of this happening, is exactly the same in both. And so they are likely to carry on doing this together. So this one is likely to move in the same way. The electrons are going to come over here. This argon will attract this other argon, and we will have an induced, we'll have temporary dipoles attracting each other. But we started off with a situation where our argon was already polarized. What if they aren't polarized? There's no reason why they should suddenly become polarized, but quantum mechanics steps in at this point. There is also no reason why they shouldn't just randomly pick up some kind of fluctuation, why they shouldn't be oscillating around anyway on their own. And the moment that one of them picks up a slight dipole, it will influence its neighbor, and they will tend to attract. This type of interaction is always attractive because there's no way for this one to not agree with this one, to go into antiphase. Why would they ever do that? They always agree with each other and attract on average. They're not attracting all of the time, but for more than half of the time, they're attracting. It's a bad example. A dipole isn't the only number of poles, because dipole just means two. We could have more poles than two. So let's imagine a bigger wave. What happens if we have a higher type of wave? Let's do a quadrupole first. A quadrupole first, or only. A quadrupole is where the electrons get spread out in one direction and squeezed in the other. That's why this is shorter in this direction and longer in this one. Why is that a quadrupole? Well, the total charge hasn't changed. So this bit is slightly negative, and this bit is slightly negative because it's got more electrons. And this bit, you can see through it easier to the argon. So this edge is slightly positive, and this edge is slightly positive, which, as you can see, is a quadrupole. It's got 4 poles, 2 pluses and 2 minuses. They're not 4 different poles, it's got 2 pluses, 2 minuses. This is exactly the same as the tides on our planet. This would be the moon. It attracts the water over towards it, but that's not the only thing that happens. As it attracts the water over towards it, there is a bulge on the other side as well. It's one of the other possible things that can happen. When we pull the water in this direction, if we come around the other side and pull it in the other direction fast enough, instead of getting just a wave on one side, we get a wave on both sides. Let us see what happens if it comes back. So we take this and it tries to come back in, this and it tries to come back in, like a drop of water or a balloon or a ball that we kick and it recovers. Try and do it like this, it will be doing this kind of thing. So let's draw the other position that we could possibly have. I'm going to rub out the signs because it'll be too ugly otherwise. So it's not quite even, but as you can see, we're oscillating between this state and this state. It's going blip, 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 blip. And that causes us to have 4 poles and they switch over. So this is minus, minus, plus, plus, and the green one is minus, minus, plus, plus. And those are changing over time. And our other argon can do exactly the same thing and also agree with it. In this case, the most attractive poles are going to be the ones that are closest together. So then in this case, the negative on this one and the positive on this one, that is or aligned to it, or they could be turned diagonally, in which case 1 plus and 1 minus will be interacting with 1 plus and 1 minus of the other one. So if we rotate this by 45 degrees, this one, so our other one would be here. So this pole would be interacting with it and this one here, and the other way around, this pole and this one here. That type of bonding can happen between any molecules at all, but it's stronger the bigger the atoms and the molecules are, because then the electrons are further away from the nuclei and they're easier to flop around. They flop around more They're easier to bully around by any charge that comes up or by any other dipole that comes up, so they influence each other stronger. That means that argon will stick to other argon quite well, but helium won't stick to other helium quite as well, because the atom is smaller, although neither of them are charged. They're both noble gases. They're both monatomic. They've only got one atom, but the argon is way bigger because it's got lots more shells in between. So the electrons on the outside are less influenced by the core. It's also the reason why Teflon with a fluorine on is less sticky in some ways than wax, because although the hydrogen is not very good at attracting things, the fluorine has a better control over its electrons because it's very, very strongly charged, and so it pulls the electrons tight to it, and that means that other things can't stick to fluorinated compounds, some fluorinated compounds, as well as they do to other materials, which is why Teflon is particularly good at repelling oil and water. Now I want to get onto bonding. So my preferred way of explaining bonding is to have orbitals and add them together, because it saves us from a few steps. If we have an orbital like this one here, this is a p orbital. The electrons, there are 2 electrons that can fit into a p orbital. The electrons are in these 2 lobes. This is an s orbital. It's spherical, so the electrons are somewhere in the sphere. Bigger s orbitals are hollow inside, so the other ones can fit and they don't interact with each other so much, but they're generally spherical in shape. They're symmetrical. If we want to make a bond, so this might be oxygen, that's why I've drawn the O on there. This might be hydrogen, so I'll just write an H on it. If we want to add them together to generate a bond, an OH bond, like in water or alcohols or something, we can add these 2 orbitals together with mathematics, and we generate new orbitals. The new orbitals will have some kind of character, but we know that OH can bond. So how are we going to connect this positive oxygen nucleus with this positive hydrogen nucleus? We need to get some electrons in the middle and not very many electrons on the outside, and that's going to pull them both in together. So we can imagine if we do that, we can generate an orbital, so a space for the electrons to go in, which is between the oxygen and the hydrogen nucleus. I haven't drawn them as circles anymore because I'm going to run out of space. So this is where our electrons are. Let's draw them as arrows up and down. That's where our 2 electrons would go if it was a bond. But we can't destroy orbitals. We started off with the 2 orbitals, and so we have to have the rest somewhere. And the rest go into an orbital which is called the antibonding orbital in this case. If there are others left over, they can also be non-bonding orbitals, but in this case we get one antibonding orbital because we had 2 orbitals. We have to generate 2. One of them is a bonding orbital. One of them is going to be the opposite. In this case, it's relatively simple in that we have a certain energy for the separate atoms. If we add them together and generate a new bonding orbital, that will reduce the energy, but our anti-bonding orbital will have exactly the same amount more energy, so worse than the bonding orbital is better, or as the bonding orbital is better, sorry. So now our little bit of weird quantum mechanics comes in. This orbital contains effectively the rest of these 2 orbitals, so it will be this bit out here, and we've pushed this one in towards the oxygen, so we're going to have to take the bit on the outside of this one too. So we end up with 2 orbitals like that, and if we put electrons into this antibonding orbital, which we could do in various ways, then they will be here, and that becomes weird because there's nothing in between, but they can jump from one end to the other because it's not very far by quantum tunneling. So they are in both ends at the same time. That is unfortunately one of the weird parts of quantum mechanics. Why do we want this? We want this because of the type of bonding that we have, and we also want this to work out how the dipole comes in a permanent dipole. So let us have a look at that here. In this bond, we've got an oxygen and a hydrogen, and this bonding orbital isn't right in the middle. It's slightly over towards the oxygen. Partly because this orbital was bigger, but mainly because the oxygen is more electronegative. It has more positive charge. It hogs the electrons. It has more positive charge and less negative charge. It hogs these electrons, so it has a slightly higher share. So it's got more than one electron effectively, and the hydrogen has slightly less than one electron, and so there is a dipole on this orbital in this direction. That's the first bit that I want to do, but also the second bit. If I want to add electrons to this bond, I have to do it into an orbital that exists. I can't just make a bond in some direction and say that's where I'm going to attach. If I have another chemical that comes along and attaches to my hydroxide or water or whatever it is, it has to attach in a direction where there's a potential for forming a bond, and this orbital or this orbital that has no electrons in it is a place where I can put electrons, and this orbital, which has electrons in it, is a place where I can steal electrons if I have something that can grab electrons off it. So this is water, which is our major substance in bionics. It's also one of the most annoying chemicals that there is because it does everything possible. This bond between hydrogen and oxygen is very charged. So the oxygen has slightly more of the electron density than the hydrogen does, and the hydrogens have less. And because it's not straight, we have a problem. First of all, we ought to explain why it's not straight. These bonds came from p orbitals, or sp3 orbitals, that's better, which are tetrahedral. And there are 4 of them, 1, 2, 3, 4. These 2 are filled with electrons and have no bonds because there's nothing attached to them. And these 2 are the bonding orbitals with hydrogen, which they've added to this hydrogen bond to form a bonding orbital. There's an anti-bonding orbital not drawn on the outside of it. Why is our water got a dipole? It's these polar bonds. So these bonds are polar, like this. And those add together, because they're pointing at each other. The vertical component counts as 0, and we end up with a little dipole in this direction. This is important because if we have another molecule, carbon dioxide, for example, that is straight, it's straight because of the orbitals that these double bonds were made out of, were p orbitals in this direction and this direction. And so they've now connected in 2 dimensions to these oxygens. That is, whoops, I can't do it. That's completely straight and flat. So this is effectively a cylinder. It has structure because there are electrons on some sides and not so many electrons on other sides. But in this direction, it's symmetrical, which means that although the oxygens also have more negative charge than the carbon, the delta stands for a bit of rather than a whole electron. This carbon dioxide is also got polar bonds, but it doesn't have a dipole. It doesn't have a dipole because minus plus minus is not a dipole in this direction, and in this direction it has no charge, and the other one as well. The water, however, is a bent molecule. It's not straight. It's a tetrahedral molecule with 2 bonds that we can't see because they've got electrons in, and that means that the water has a permanent dipole, which means that if some argon comes along, it will manipulate the argon so that it can stick to it. So we've had the weakest type of bond, which is a temporary dipole with a temporary dipole. The next weakest type of bond, which is a temporary dipole with a permanent dipole. Now we get to two permanent dipoles interacting, which would be water stacking in this direction with its plus minus, plus minus, plus minus, like little magnets all in a row. They'll all stick together. It's not going to be a permanent situation because that would be not very fluid. So we would lose possibilities. We'd lose possibilities of configuration. We'd lose possibilities of motion. We'd lose possibilities of rotation. So that is unlikely to happen thermodynamically unless we're really, really cold. So at normal temperatures, water molecules are rotating very fast indeed. However, they spend more time aligned with each other, either both in this direction or both in this direction, than they do anti-aligned with each other. And that means that on average, they tend to attract. Likewise, if I take my pen, here's a pen. If I take my pen and, oh, here's a pen. If I take my pen and I go up to a water tap faucet, if you turn it on to very low rate and you bring a pen up to it or a ruler, first of all, give it a rub on a fleece. That's a good thing to use. Give it a rub on a fleece, bring it up to it. You can bend the stream of the tap towards the ruler, always. It doesn't matter whether it's a ruler or a pen. In school or in physics, you may have done the experiment that some polymers become positively charged and some polymers become negatively charged when you rub them. It doesn't actually make a difference with water which you bring up because the water rotates to mostly point towards the correct direction for the polymer that you bring up. So if we bring up a positive charge, it would rotate so that we're coming from here effectively, and if we bring up a negatively charge, it would rotate to look like this, that it's attracting the positive end. So our dipoles will then all rotate and it will all be happy. Another thing you might have seen in physics is that the relative permittivity of water is odd, that if we take a capacitor and we put nothing in between, so let's have a capacitor. If we take a capacitor plus minus and we put nothing in between, we can get a certain amount of charge on it per volt. If we put water in between, the water aligns. So let's have the water align. Let's just draw little arrows. The water aligns to agree with the arrows, and that reduces the effective voltage on the electrode, the effective voltage per electron, because these positive charges are helping our electrons to stick and these negative ends are helping our holes, the lack of electrons, to stick, the positive charge, and therefore we can fit more charge on for the same voltage, so our capacitance goes up. Capacitance of a capacitor full of water is about 80 times as high as a capacitance full of nothing, vacuum. That is because water has a relatively high dipole and it's very easy to manipulate it so that it sticks, so that it points in the correct direction. So now we've effectively got a lot of different types of bonding if we combine all of the possibilities. So we can have a charge interacting with a temporary dipole or a dipole. We can have a dipole interacting with a temporary dipole or a dipole. And we can have a temporary dipole interacting with another temporary dipole. Now we have the next one up, which would be an actual bond. It's not a proper bond, but an actual bond. So as we recall, you recall, there was this anti-bonding orbital on the end of this hydrogen. Out here, there's one out here as well. But remember, this oxygen has too many electrons effectively, and this hydrogen has too few because the ones in the bond are over towards the oxygen. So we can do effectively a chemical reaction where we put these electrons into this orbital and make a new bond. Let's do that temporarily. Now let's do that next step. So now I've put the electrons that used to be in this, what's called a lone pair, in this extra orbital, into the hydrogen, or into a bonding orbital with the hydrogen, just like the OH bond, a new OH bond. That has caused us two new problems, and we can't stop there, because what we've now got is hydrogen with too many bonds. Whoops. And this hydrogen has two bonding orbitals and two anti-bonding orbitals, which are all full, which is terrible. We also have a charge problem. This oxygen has positive charge because it gave away its electrons. And this hydrogen, or this oxygen, depending on where we put the charge, has a negative charge, which is also unhappy. So we've got to do something about it. One thing we could do is break this bond and give the electrons to the oxygen over there. Sorry about leaning over myself, but there we go. Let me get out of the way. So now we've made an OH minus ion, and we've made an H3O plus. This is what we refer to in chemistry as H plus. It's actually H3O plus, and this is an OH minus ion. So this is what could happen. This water could steal a hydrogen off the other water. But what we're interested in for the purposes of today is it now going back. So it can do that. Then it can go back instantly as possible. So this oxygen has too many electrons, so it goes back to here, and this bond breaks, and that resolves our charge problem again. And we get back to where we started with no charge and two waters. But because we can occasionally make a bond to that hydrogen, a proper bond, that's a full bond, but it's not present all the time. So we can make a proper bond, but we're not making a bond that stays there. It forms and breaks and forms and breaks. And that process means that these two waters are held at exactly the right distance to do that for a reasonable amount of time. That generates a force that holds our water molecules together, and it's a very strong force. What we notice about this is several things. First of all, water boils at a much higher temperature than you would expect for an equivalent molecule of the same mass with the same dipole moment. So an equivalent molecule of the same mass with the same dipole moment might be hydrogen chloride. And hydrogen chloride is a gas at room temperature. Water, as you've noticed, is not a gas at room temperature. It's mostly liquid. So there is a water vapor present. You can get ice forming if your room's really cold, but most of the time water is a liquid to us. Hydrogen chloride is most of the time a gas. If it's quite cold, we can freeze it, but we have to get down to very low temperatures to do that, or even to liquefy it. Whoops. What we also notice from this is that the direction is different. So this is a tetrahedron, this here. This direction is up, this is down. This is also in two other directions. Whoops, I can't get my fingers in front of the camera. So we've got a tripod effectively, and my arm is the other side. We've got four things going in different directions in 3 dimensions. So these, we could say, are flat in this whiteboard, and this one comes out, this one goes down. To connect to it, we have to go straight into the end of the hydrogen, because that's where the anti-bonding orbital is. That's the only direction that we can attack it from, because there are no open orbitals anywhere else for us to put those electrons in, which means that we have to attack it straight. So there has to be a tetrahedral geometry, and this one has to be rotated, and it has to be so that the hydrogen is pointing towards one of these lone pairs. That is not the same direction as this, which is stacked up like cups or like magnets. And what you can see hand-wavingly, but not entirely true, is an explanation of why water expands when it freezes. As we cool the water down and it starts to freeze, we tend to make more of these bonds, which are tetrahedral in nature and leave this space empty, instead of these types of bonds, which are stacking in nature and much, much more efficient in space. That's not entirely true, and we've also got a dimensions problem, because not only are these things moving around all the time in liquid water, the crystal of the ice is not usually perfect, and there's another dimension out here, so there's no reason for this to not rotate in this direction, and it still has its dipole moment aligned. So we've got all kinds of things going on. Reality is always more complicated, but on average, the distance between water molecules is smaller in the liquid than it is in the solid, and the more hydrogen bonding that we have, the more space we leave in our structure. So much so that, as you might have heard, if we freeze water, we can hide things inside it. So inside this hole, because there's another water here, so there's a hole here. Inside that hole, we can fit other molecules such as methane, for example. So under the sea, mostly in Russia, but also in Asia, under the sea there are stores of gas in ice, and the gas molecules are stuck in this cage. They're called clathrate cages. When you melt the ice, the gas escapes and you can burn it. A more trivial but fun way of using it is what's used as fizzy lollipops. If we freeze water in the presence of a high pressure of carbon dioxide, we can get carbon dioxide molecules to go in this hole. If we freeze water normally with carbon dioxide in it, as it freezes, it pushes the gas out. So we didn't draw that in our freezing part. But if there is gas dissolved in the water, when you freeze it, it comes out as bubbles, which is why ice very, very often has bubbles in it. What we don't see is the dissolved gas staying in the water. So when you melt your ice, it tastes slightly different because of the difference in dissolved gas. But if we freeze it at a high pressure of carbon dioxide and then let the pressure off, the carbon dioxide can be stuck in these cages, mostly stuck in these cages, and then we can store it, put it into ice lollies, for example, maybe flavor them cola and lemon flavor, and then when you try to lick them, you make it warm, the ice melts, and the carbon dioxide bubbles out, so you get a frozen fizzy effect. But what it is way cooler than a frozen fizzy effect. It's carbon dioxide molecules trapped in little ice cages. So now we have several types of bonding, intermolecular, meaning between different molecules. We can have our temporary dipoles, which are the weakest ones. We can have a dipole with a dipole. We can have a dipole with a temporary dipole. We can have hydrogen bonding, and then over here, for a reason that will become apparent in a moment, we have a charge. So if we dissolve some salt in some water, some sodium ions and some chloride ions, they will also interact with the water in different ways. They can generate a temporary dipole. It's not necessary in water, but they could. They can interact with the dipole. There's a dotted line to the hydrogen bonding because they can't really do hydrogen bonding, but they can interact with it. However, there's a different distance question. So how far can these things reach? If we take a simple case, which is charge, you might know about it. So charge is a simple case because it's mathematically simple. The two charges interact with each other with... So what I was trying to say before I ran out of words to fill it up was that Coulomb's law, that was the thing that I couldn't think of. Coulomb's law tells us the interaction between two charges. So two charges interact in an effectively inverse square fashion the charge on one thing, the charge on the other thing, divided by the distance squared. That would be what we would expect for a charge interacting with another charge. If we take a dipole, we can imagine, without having to derive it mathematically, that a dipole will decay much faster than that, because if we have a dipole over here, let's have a dipole this way, probably easier this way around, plus, let's check my sound is on, yeah, plus minus, so it's pointing in this direction. If we're right close to it, so here, we can see, so if we put a charge close to it, let's have it this way, we can see that it's going to be attracted at this distance, and it's going to be also repelled at this distance, and this is the hypotenuse, effectively, of a right-angled triangle. This is the best, well, no, it's not quite the best it can be over here. Let us move our positive charge right over here, and we can see that the difference between the two distances is now smaller. If we make it better by moving it right down to below, so our triangle collapses because we've made it very small. So we can put our positive charge right down here. Whoops, that's not on the screen, here. Then the two distances differ by the length of the molecule. And obviously, the further away we are, the proportional distance will go down. So the difference between this length and this length goes down as we go further away, and it goes down as we go further away here. And the best we can possibly do is the length of the molecule. Typically, the dipole isn't as long as the molecule, as with our water. That's not on the board. So as with our water, the dipole length, the dipole is only as long as part of the molecule, because it's not the length, the longest distance across the molecule. My green screen is breaking down, I see. So our dipole-dipole interaction will not, or will decay in strength much faster than a charge-charge interaction, which decays at the square of the distance, and that's good because the square of the distance is a long-range interaction. Charge-charge interaction is quite long range. A temporary dipole has to first of all agree with the other dipole. So that is going to go down even faster, because if we get to a distance where they can't see each other so much, even if they are dipoles, then they're not even going to form dipoles. And so the strength will go down faster with the temporary dipole interaction. If we go up to the top one here, hydrogen bonding, that has a length. It can only form a bond at approximately the bond length. The orbital that we're going from and coming to, oh yeah, that is on there. So the oxygen orbital with the lone pair of electrons in has a certain size, so that has a length. And the hydrogen antibonding orbital, the hydrogen-oxygen antibonding orbital, has a length too, so they can overlap just at the end, or they could have proper overlap and be very strong. So there is a length range for the hydrogen bond, but beyond that range, we can't form a hydrogen bond at all. So that is going to go down more suddenly with distance than any of the others, but the temporary dipole is the one that has the shortest effective range, unless we have a lot of particles. That is important because it means that charge-charge interactions will happen much further through our solution than any other of these effects. And it's also important to remember that they're not very long-range effects, so that we can understand that when a water molecule, for example, leaves the surface of water, it is very quickly not being attracted with any of, oops, sorry, my hand is up here, with any of these three effects and any combined attraction between these two here. So now let's go on to see how this generates an emerging effect, which is surface tension. So now we have some water in a pot, and we're thinking about what could possibly happen here. So we've got a water molecule in the middle here, and it can have dipole-dipole interaction with the ones on this side and the ones behind it. And it can have hydrogen bonding interaction in any direction that it feels like, but in this moment it can only have dipole-dipole interaction with the ones in front and behind, and this one that's turned 90 degrees is obviously on the top and the bottom. It's being pulled by the bonding and by the hydrogen bonding and by non-polar interactions, if it has any. In the case of water, the other ones are so much stronger that we don't need to worry about it, but they are being pulled in both directions, and so they don't go anywhere due to these forces. If we have them on the surface, however, we have an imbalance because there aren't any molecules above in a approximation. So we've got a water molecule at the surface, it's interacting with water molecules below it and to the side of it, because it can rotate between these two states. So it can see all of these molecules below and around it. If they're all the same size, we could just draw them in. But there aren't any on the top. Because there aren't any on the top, there's a missing force. And so just the same as we were doing with the bubbles, there's a resulting force. So we add these two together. We add all of these vectors effectively together. Let's have one slightly diagonal to try to reduce it. Then we end up with a net force that goes downwards. That's our net force. If we part the water, let's put it like that. So if we cut the water here and try to pull it apart, then we will end up, first of all, having to break the bonding between these molecules that are there in the surface. And this generates our emerging effect, which is surface tension, that it appears that there is a skin on the surface of the water pulling in. There isn't really. There's just an attraction between the molecules, and at the surface it's not fully balanced because there aren't other molecules all the way around it. Yeah, so that'll do for today. I think that's enough content for one time. I'll see you next time for the next installment of Bionics of Surfaces. Stuff that sticks in that case.